you. Yes, I slightly changed the title. I'm sorry about that. I recently learned that kinematic spaces is already used for a specific space, and the spaces I'll present are slightly different. So I'd like to thank the organizers for the opportunity to present this work. Unfortunately, not in person, but nonetheless, I'm very grateful to have this opportunity. So I'm going to give you, I start with the motivation of what's behind the scenes happening in physics. So within physics, we're in the part of particle physics, of scattering amplitudes and quantum field theories. So the idea here is that scattering amplitudes are functions that compute probabilities of particle interactions. And for physicists, it's really important to understand these functions that are eventually the research outcomes are used even in the experiments. So for me, it will be useful to just understand the very basics of the scattering amplitude as a function on some space. I call it kinematic space, and I'll tell you later what this space is, but it's a space whose points represent particle configurations. These functions are typically generalized polylogarithms, and they can be expressed in iterated integrals. And there's lots of machinery, lots of research going on in understanding these types of functions better. I'm not on that side of the story, but I want to give you just a brief idea of how it connects with what I will present. So here's an example of the die logarithm and how I can express it as an iterated integral. And then instead of dealing with the whole integral, I can consider it symbol, which essentially just reads off the information of the integration kernels and forgets about potentially the coefficients. So in the case of Li2, what I get is just the arguments of the d logs that appear in the iterated integrals. So its symbol is this, well, it's written as a tensor product here, but you might as well just think about it as a set of letters. So the elements appearing here, the functions are called letters. And so this is one way to reduce the information, to capture part of the information of the scattering amplitude in a more compact way. And understanding scattering amplitudes this way has led to a bootstrap program where people from scratch, given this set of letters or the symbol, search the space of all functions on the corresponding kinematic space for functions, generalized polylogs that have this symbol. So that's the idea behind a bootstrap program that was developed by Lance Dixon and many collaborators. And now we enter the part of the story where my work connects to, and that is a funny observation that was made about 10 years ago by Goncharov, Volovic, Virgu, and Spratlin, that discovered that in fact the symbol of the scattering amplitude in a particular toy model that's called planar n equals 4 super Yang-Mills, when we consider 6 particles or 7 particles, in fact, the symbol coincides with a certain set of cluster variables, or in these cases, the whole set of cluster variables on the Grassmannian. So the Grassmannian 4n in this case is the kinematic space. That's the space where a point represents a particle configuration. And so from this observation, there has been more progress in the bootstrap program, working with cluster structures of Grassmannians of higher n, and running this bootstrap to see if there's a unique solution coming up for the amplitude. Here's a long list of references of people that have contributed. So the first one here is the paper I mentioned that started this connection with cluster algebras. And then you can see Dixon popping up a lot with lots of different collaborators. And the variations here on the side is like different parts of the story, varying maximally helicity violating configurations or next to it. And hexagon is 6 points, heptagon is 7 points or seven particles. So I entered this story quite late. All of this work has already been done. But as a mathematician, for me, like a natural question at this point was just, okay, what happens beyond this very nice toy model of planar n equals 4 super Yang-Mills? We could ask, what are the corresponding kinematic spaces or the varieties? Are there also algebraic varieties? and other cluster structures that could potentially be useful to extend the bootstrap program beyond n equals 4 superyoung. Okay, are there any questions regarding the motivation? Or comments also, in case there's people in the audience more familiar with the subject than me. Okay, so if that's not the case, let me move on, and I will tell you the outline for the rest of the talk. Well, in math, the next best thing to a Grassmannian is a partial flag variety, so we'll be moving to this class of spaces. Then I'll tell you about the spinor, helicity, and momentum twistor varieties that arise as partial flag varieties, the cluster algebra structures, and then I'll end with some results that we made that are on the math side, just about the cluster structures that we find and how they're related to Grassmannian cluster structures. And I'll end with a little summary and an outlook of what we're going to do next. So partial flag variety, in case you haven't seen one before, as a set, the input I need to define a partial flag variety is 3 integers in this case, because I'm just going to talk about 2-step partial flag varieties. So I'm going to take integers d1 and d2, and n is going to determine the dimension of an ambient vector space. And in this vector space, I consider flags of subvector spaces v1, v2, such that vi is of dimension di. Now, for me, it's going to be easier to represent a flag by a matrix, and I can do that by first fixing a basis of the ambient vector space, and then fixing bases for the vector spaces in my flag, expressing them in the fixed basis of c to the n, and I write down these expressions in a matrix so that row-wise, this matrix MV would generate my flag. So the first di rows generate the vector space V1, and the first D2, or the last D2, or all the rows, sorry, my matrix will be until D2, actually this is a typo here, generate the vector space V2. And once I've done that, I can start parametrizing the flag variety by Plucker coordinates, which are just minors of this matrix, and the sizes of the minors will exactly be D1 or D2. So here's a little example. If my flag variety is, for example, 2, 3 in 2, 3 in C4, then this could be a matrix representing a flag. The first 2 rows span a 2-dimensional vector space. The whole matrix is of full rank, spanning a 3-dimensional vector space in C4. And well, yeah, the Plucker coordinate 1, 3, 4 would pick out the first, the third, and the fourth column and compute the determinant of the matrix. So the Plucker coordinates are not independent. They satisfy determinantal relations called Plucker relations, and they define for me an embedding of the partial flag variety into a product of 2 projective spaces, where the Plucker coordinates are exactly the homogeneous coordinates of these spaces. And a very important player in the story I'm telling you is going to be the homogeneous coordinate ring or multi-homogeneous coordinate ring of these partial flag varieties with respect to the Plucker embedding. Okay, so with this as having said, sorry if I'm boring the experts, let me move on and tell you about the kinds of varieties that are of interest in the physical applications. So I'm going to start here with Minkowski space, space-time R4 with the inner product, first variable corresponding to time, the last 3 variables corresponding to space coordinates. And if I take a point in R4, it would represent a particle, and I can associate with it its helicity spinor. That's a 2x2 complex matrix that I obtained from the coordinates P0 up to P3 in the following form. And it has the advantage, or it has like the interesting property that the matrix on the right decomposes. I can write it as a product of 2 vectors with complex entries, and these are the vectors lambda, lambda, tilde. So this matrix you see on the right, I can recover it from lambda and lambda tilde by multiplying lambda with lambda tilde transpose. And the good thing, or one good thing about this parametrization, is that it remembers very compactly what's the mass of my particle. So in general, the mass of my particle satisfies that p squared is m squared, m being the mass, and p squared is physics notation for taking the inner product of p with itself. And the particle is light-like if its mass is 0. And this is captured by the determinant of this matrix. So in particular, if lambda times lambda tilde transpose is 0, this is the helicity spinor, or the decomposition of a helicity spinor of mass 0.
So okay, it depends from P0 and P3 only to the sum. It's bizarre.
Yes.
Only the sum of P0 and P3. Okay. So it's
So yeah. Sorry, what?
Degenerate map, yeah. So it's going to have the same spinor, yeah.
Yes.
Okay. Okay.
Okay. Good. Right. So, so having this formalism of passing from a particle to its helicity spinor, I can define a space that models particle configurations. So I'll just do the same formalism, but now I start with a set of n particles to
Can you
each.
when you go back, yeah?
Yes.
Yeah. I don't like a formal because maybe P0 minus P3 in one of entries of this sigma.
Oh, I see. In here, you say, right?
Yes, because the terminal will be P0 square minus P3 square.
Right. Yeah, there's a typo somewhere.
Yeah.
I guess on this side. Yeah.
In
But
matrix, it should be not the same.
yeah, you're absolutely right. Yeah, I'm sorry about that. Yeah. Okay. But okay, so let's say up to fixing some entries here, we can associate lambda and lambda tilde to P in R3 and R4. And yeah, so this is what I will be doing now for a set of n particles. I get for every particle this pair, lambda I tilde, corresponding to the particle pi. All of them satisfy lambda I tilde transpose is 0. And I'm going to stack these in matrices, capital lambda tilde. These matrices are going to be in full rank. So I can think of them as points in the Grassmannian 2n. And they will satisfy that if I multiply lambda with lambda tilde transpose, I still get the 0 matrix. And this is the motivation to define the following space called the spinor helicity variety. So inside the product of two Grassmannians 2n, I take pairs such that in matrix representation, lambda times lambda tilde transpose is 0. And well, again, we're talking about a space that's parameterized, where I can express points as matrices, so I can parameterize by minors. And I'm gonna choose the following notation. Pij is gonna denote 2 by 2 minor of the first matrix, and Pij tilde 2 by 2 minor of the second matrix. And in this way, I get the spinor helicity variety inside a product of two projective spaces. The identities that these elements, or that the parameters satisfy, that vanish on my space, are called Schouten identities in physics, but these are just Plücker relations of 2 by 2 minors on each side. And then I have relations between the two sets of Plückers that come from momentum conservation, and they are of this form. Okay, good. So, well, if you're familiar with flag varieties, and these spaces already look a lot like flag varieties, and here's the map that realizes the spinor helicity variety as a flag variety. So okay, so I changed notation here. These should be PIJs. This is the notation you would find in the physics literature for the 2 by 2 minors of the two different matrices. But the takeaway being that I will identify the PIJs just with PIJs, and the PIJ tilde with minors of size n-2, taking into account a sign. Then the Plücker, then the relations I had on the first slide here, on the slide before, just transform to usual Plücker relations that hold inside a flag variety, and the flag variety in this case is the one of dimensions 2 and n minus 2 in c to the n. And then the spinor helicity variety has been studied, in fact, a larger class of spaces where I can vary also the sizes of the matrices and the ranks of the outcome if I take the product. That's been studied by Massless, Pfister, and Sturmfeld. So we know the dimension of the space and we know the dimension of the flag variety, the two coincide. So this is in fact an isomorphism. So the first takeaway is that the spinor helicity formalism gives us a two-step flag variety, 2 n minus 2 in c to the n. Now there's the second formalism I can take, and that is given the particle configuration, passing to momentum twistor space. So that means that for each particle that was an element in R4, I go to its momentum twistor that lives in CP3. So I get a configuration of endpoints in CP3. And this system, again, I can parametrize it by taking minors of this matrix. This looks like the Grassmannian 4n, just that I have to allow column scaling because my main points are in CP3. And this is the formalism that has been first used to relate to cluster algebras or to the Grassmannian in general. Now, if I play the game just in this case, this will be the model for n equals 4 super Young mills. There's lots of symmetries in here. For example, I have a cyclic symmetry around my particles. But there are some ways how we can kind of twerk this configuration to get rid of some of these symmetries. And one way physicists do that is by introducing what they call a line at infinity or an infinity twistor. So to my configuration of endpoints, I will add 2 more points, Zn plus 1 and Zn plus 2, but I will require my configuration or the functions that I'm interested in are only the ones depending on the n points Z1 until Zn, or the line spanned by Zn plus 1 and Zn plus 2. So if I start parametrizing this space, this can be encoded in the following way. So I would take determinants of my matrix whose columns are Z1 until Zn plus 2. I take 4 minors in there, but I only allow the indices to range from 1 to n. So I only take 4 minors of the first endpoints, or I take 4 minors where the last 2 columns are contained together. So you would never have any minor here that would just take Zn plus 1 or just Zn plus 2 separately. Is this clear? Okay, so then what I will do here is, motivated by this model, I define the momentum twistor variety. I will define it as a subvariety of a product of 2 projective spaces, and I will define it as the vanishing set of all the determinantal identities I can observe between these 2 sets of minors. And then it's not hard to see that the identities I get are exactly those that were satisfied by a partial flag variety with dimensions 2 and 4 in c to the n. So this is another way how to get to a partial flag variety using momentum twistors. Okay. Any questions on these 2 spaces? How do I get there? Okay. Otherwise, feel free to interrupt me at any point. So then I wasn't exactly sure how much I could assume that people know what cluster algebra. So I prepared like 2 very brief introductory slides to the subject. Or maybe we could actually do a quick raise of hands if people know cluster algebras in the audience.
Okay.
Glad knows. Yeah. Okay, so let me do the quick summary. So cluster algebras are certain commutative algebras that have very special combinatorial structure. The first special thing is that they have special generators that are called the cluster variables, and they're grouped together in clusters. Clusters are maximal sets of algebraically independent elements. And they have special automorphisms, which are called mutations. And these automorphisms take a cluster and send it to another. And the whole data of a cluster algebra is encoded in a quiver, which is a directed graph without loops and two cycles. So I'm not in the most general setting of cluster algebras here. And this is everyone's first example of cluster algebras. So the quiver I would have here just has two vertices and one arrow, it's an A2 quiver. And the mutation rule is can be written in the following form. So for my cluster algebra, I would start with a tuple x1, x2 of variables that I associate to the vertices of my quiver. And I have this recursive rule of how to generate new clusters from old ones. And my clusters will all be of form xi and xi plus 1. So if I start playing this mutation game, in this case, it's actually not that interesting because after a few steps of mutation, I realize that the sixth variable was already present before. So the whole system is periodic. I get back to the first cluster variable x1, and then I get back to x2. And in total, I just have 5 different cluster variables. And now the cluster algebra is defined, and this will be the case in general, inside the field of rational functions of some cluster that I fixed initially. And it's generated by all the cluster variables I encounter playing this game of mutation in all different directions. So in this case, I only have these 5 elements inside the ring of rational functions and 2 variables. And this is my cluster algebra. So more generally, the mutation rule is encoded locally in my quiver. This is a little diagram that very, how do you say, like it captures all the information of the mutation rule very efficiently. The mutation is a local operation in this quiver. So I start by fixing some vertex in the quiver. In this case, it would be K. And then I consider all neighboring vertices that have arrows into K or out of K, so that I can form paths of lengths 2 passing through K. And for every such path from I to J, I add a direct arrow going from J to I after the mutation. So here, my notation is that C would be the number of arrows from I to J, but C could be negative, which would which would represent arrows from J to I. And then I would add in all these arrows, A times B many paths in this case. But after adding in the arrows, remember I mentioned that my quiver should not have any 2 cycles. So after adding in these extra arrows, I delete a maximal collection of 2 cycles that I might have formed. And this is how C plus AB will be exactly the right number of arrows afterwards. So if C was negative, I have some cancellation happening. And otherwise, I just get more arrows from I to J. And the second ingredient of the mutation is a change of variables. So I would change cluster variables to every vertex in the quiver. And after mutation, I will replace exactly the variable that was associated to my kth vertex. And the way I replace it is also encoded in the quiver. So the new variable xk that appears in my tuple after mutation, I get it as from the following binomial. I take the product of all the variables xi that are corresponding to vertices or arrows that go from I to k. And I take a monomial of all the variables xj that correspond to arrows going from k to j, and I divide the whole expression by xk. Okay. And the whole configuration of the quiver with the tuple of vertices is what is called a seed. Are there any questions by the non-experts or the experts? Okay, great. So the takeaway of this definition is the following. To define a cluster algebra, all I need is a quiver, a directed graph with no loops and no 2 cycles, and a tuple of algebraically independent elements, 1 for each vertex in my quiver, that lie inside a field of rational functions. and the mutation rule that is then encoded in the quiver as well. And why am I telling you all this? Well, the ring, the homogeneous coordinate ring of a flag variety, is an example of a cluster algebra. And this has been shown by guys Leclerc and Schur back in 2008. Okay, so here, remember, I had the flag varieties. I embedded them with a Pluk embedding and a product of projective spaces. And the multi-homogeneous coordinate ring of this embedding is a cluster algebra. And for the rest of the talk, I want to tell you first how to construct, what's the initial data that you need to construct this homogeneous coordinate ring as a cluster algebra, and then what we can say about the cluster structure and how it relates to the cluster structure of Grassmannian.
Okay. Small question.
Yes.
So if D1 is not equal D2 minus 1, then we don't have this purity phenomenon which we have for Planck varieties and for Grassmannian. So it does not matter for existence cluster structure because positivity, it will be some problem with positivity.
What would be, so if D1 is...
Yeah, so if D2 is not equal D1 plus 1,
yes,
then we have no purity conditions. So if we consider just minors, and then make Greek permutations, then it would be not pure in the sense that some of minors, which forms like pure commuting families, will be not of full rank. So it does not matter for this theorem.
So this theorem holds actually more general for any selection of D1 to DK. So an arbitrary partial flag variety.
Yeah, but the same effect. So if you have gaps, then
yes.
there is problem with purity in quasi-commuting. So if you just consider instead of minors, quantum minors, then they will not, and you will consider a family of quasi-commuting families of quantum minors. Then if you have gaps between D, then it will be not complex. So they will be of different dimension.
Oh, interesting. I'm not familiar with this part of the story, but also we'll see on the next slide that having gaps actually changes, makes the cluster structure, I would say, more interesting. But not having gaps is essentially the case of the full flag variety, just with some extra minors in the end. But as soon as we have gaps, also the types of cluster variables we get already in the initial seed changes. But the theorem is even more general. It's for groups of type ADE and partial flag varieties in there. Okay, let me give you the combinatorial construction of how to get to the initial seeds. I need to tell you what's the quiver to start with and what's the set of cluster variables I associate with the vertices. And I'm going to spend quite some time on this diagram. So I'm going to do all of this in an example that I hope is sufficiently large enough to see the phenomenon. So I'm going to talk about the flag variety of 2, 5, 7. So it's 2-dimensional vector spaces in a 5-dimensional vector space and C to the 7. And I start out by drawing a wiring diagram. So on the bottom here, I have my indices 1 to 7, and I just remember which are the ones that are actually supported in my flag as dimensions. And then I draw a permutation, and this is actually the permutation that determines the parabolic group that I need to quotient by SLN by the parabolic group corresponding to this permutation is the partial flag variety. But if you're not familiar with this story, all you can do it completely combinatorially. So we will consider all the indices up until D1, and we will draw the lines parallel. They will not cross, and then they just go into the last slots. So in this case, 7 is n, right? So we go 1 goes to 6 and 2 goes to 7. And then we take the next block of lines starting at D1 plus 1 going up until D2. Again, the lines will not cross. They would just go up straight and turn left once. And wherever they end up, in this case, actually the same spots as before, 5, 4, 3. This is their configuration. And then we do the same with the last tuple of lines. So we run from D2 until n, go up and turn left once without having these lines cross. And in general, you would just have more indices or more lines marked down here, and you would proceed the same way. Constructing this permutation where within the blocks, the lines will not cross. Then there's extra information here that is inside the bounded regions and regions that are unbounded to the left. So have all these regions always between the lines, or in this case, just the heights I and I plus 1. And inside here, I have all these bounded regions. And the indices that I've written down in the regions always correspond to the lines that are either passing on top or to the right of the line. So like northeast of my region. So this one, for example, this whole region corresponds just to the next 5, because that's the only line passing to this northeast. Could pick out this line maybe. So here I have on top the line 4, to the right the line 2, and then also further out the line 5. So this is the region I would associate it with index set 2, 4, 5. And all of these form vertices of my quiver, all of these regions, bounded or unbounded to the left. Then I have 2 extra vertices that I need to make everything homogeneous afterwards. And they correspond exactly to the tuples or to the marked points in my number, so to the dimensions present in my flag. And then the rule for the quiver is also quite combinatorial when you focus on maybe just this bounded region here with index set 2, 4, 5. Then I have arrows coming into this vertex, or whenever I have a line segment that is horizontal, I have a vertical arrow going down. So this is this one from 2, 5 to 2, 4, 5, from 2, 4, 5 to 2, 3, 4, 5. And whenever I have this was the horizontal line segments. And whenever I have a vertical line segments, like to the left and to the right of this box, then I have an arrow from left to right. So here I have one from 1, 2, 4, 5 to 2, 4, 5, and to 4, 5. And then there's diagonal arrows that pass through the crossings from the southeast to the northwest. So this is this arrow. And then again, I have these 2 extra vertices that are not exactly a part of this rule, that don't fit this rule. But yeah, you can also combinatorially, you can see how they are connected. So whenever I have a line here, this horizontal line, this vertical line, sorry, that corresponds to D2, I go to the point where it crosses the line D2 plus 1. And I will connect the 2 vertices corresponding to the adjacent, like opposite adjacent regions of this crossing, and I make this configuration. Here, I don't have the next region anymore, so this arrow from 5, 7 to what's noted omega 5 here would just be the arrow corresponding to this arrow. And as there is no more region on this side of the crossing, I don't have the other arrow. Any questions about how I get to this diagram or the index sets?
It's of dimension 5, it's intervals.
Yes, so the index sets appearing are always unions of 2 intervals, and the intervals always run onto di, so one of the di's, or n. So here, for example, 5, 7, I would understand it as the union of the interval of just 5 and just 7. 5, so they always end at my mark points, and you can think of n being the next mark point. So yeah, for example, this one is the sorry?
It's just from Grassmannian, but it's for size 5, so only just 2 sets, and for size 2, yeah, 4 elements.
Yeah, this also works for Grassmannians. The same construction where we just have one mark.
Yeah, 2 element, just 4 from 2, and 2 from 5, and the 6 element from the fiber 5 and 2. Yeah.
So I didn't quite get that.
Two element sets is just from Grassmannian of 2, 7 and 5.
Yeah, let me move on. So these are not yet index sets of Plücker coordinates or something like that, but they're very closely related. If that's maybe where you're going. So these index sets, I understand them as being the row sets of minors on an upper triangular unipotent matrix. So maybe let me move on to the next slide and tell you how to get to Plücker coordinates or Plücker expressions from these collection of index sets. This is essentially just a Laplace formula. So as you observe, the index sets that appear in my diagram, they're always of this form union of two intervals, and the intervals end in one of my dimensions, di, or they could also end in n. And I understand these index sets, so they represent the row set of minors of an n by n unipotent upper triangular matrix. And I would like to translate them to Plücker coordinates. And the way to do it is just using a Laplace formula. So all these minors, in general, such a minor will have a quadratic expression in Plücker coordinates. And here I understand the Plücker coordinates also as minors on this n by n unipotent triangular matrix, just that they are top bound. So here the index set in the Plücker, remember that was a column set on the matrix, and this index set is a row set. And the column set here is always right bound, and the row set here is always top bound. So here we start from 1 to cardinality, and here I run up from whatever I need to get the right cardinality until n. And this is the translation between the two. And then just before I get back to the example, to have everything a bit more condensed, I will not write the whole expression of Plückers I compute here in my diagram. Instead, what I do is on the right-hand side, each of those products of Plückers, I will just remember their index sets and write them in a Young diagram. It will turn out that there's a way to do this just with standard monomials. So I'll actually get Young tableau on the right-hand side, and then I take the weak order of tableau to just choose the maximal one. And it turns out, in fact, that if I do this with my cluster variables, the tableau I get is in fact the tableau that corresponds to this cluster variable as an element of Lustig-Stuhl canonical basis. And there's a character formula of how to recover the whole expression of the cluster variable in terms of Plückers given the tableau. So to have everything more concise, let me introduce the notation of T, D1, D2, N to denote the set of semi-standard Young tableau with columns of size either D1 or D2 and filling 1 to N. And then similarly for a Grassmannian, I would just have TDN, so just tableaus with columns of size or length D and entries 1 to N. So if I do that in my example from before, this is what I get. On the very top, I only get 2 Plückers, so Plückers of size 2. On the very bottom, I only get Plückers of size 5. And then where these two regions meet, I actually get quadratic expressions on the right-hand side of this expansion formula. And this is the set of tableau that I would associate. And if you were in a Grassmannian, all of this would just be one column tableau corresponding to Plücker coordinates. Did this clear up your question, Gleb?
How many of them? Dimension by what?
Sorry.
So how many variables? 14?
How many variables? Oh, the dimension, I think in this case, this would be, I have the formula here, right? Let me just go back. The spinor helicity formula to here, 4 times n minus 3 plus 2. So this example is also of the case 2 n minus 2n. So we have 4 times n minus 3, and then plus 2 are the ones that I introduced just to make everything homogeneous. Let me see if I can easily scroll back. Here. Yeah. So you can count that this is the right number. Right. Okay. So then let me, for the last 2 minutes, tell you about an interesting relation that we found between these cluster structures of partial flag varieties and the cluster structures for Grassmannians. And it comes from an observation on the set of Young tableau that we associate to the elements of the cluster algebra or its holistic dual canonical basis. So if we have tableau with columns of 2 different sizes, D1, D2, and filling up to n, we can embed them into the set of tableau with columns only of size D2, but here I increase n by the difference of D2 and D1. So the way to think about this is if you have a column in your tableau that just has size D2, so D2 many boxes or D2 many entries, then you just keep it. And if you have a column of size just D1, then you fill up with the indices you need to make it a column of size D2. So just as an example, if you have tableau 2, 4 filled with indices until 6, you can embed into tableau of column size 4 with filling up until 8. A tableau of length 2, you just fill it up with 7 and 8, and a tableau of length 4, you just keep it. Okay, so this is what happens on the columns, and you extend it to tableau. And then the observation we made is the following. If we start with the partial flag variety 2, n minus 2n, or 2, 4n, so these are the 2 cases relevant from the physics. And I will denote by S not F this initial seed that I've constructed with the quiver and its set of cluster variables. Then for the corresponding Grassmannian that I get here on the right-hand side, I can find a seed as GR, so quiver QGR, and the tuple of indices, so that the quiver for the flag variety, the initial quiver, is a full subquiver in the Grassmannian. So I can get it by freezing, in this case, n minus 5 or respectively 1 vertices, and eliminating a certain number of vertices. And this map, this combinatorial map phi, is such that if I apply it to the tableau representing my cluster variables, they go to exactly the tableau of the cluster variables sitting at the same knot in the Grassmannian. So this combinatorial embedding identifies the cluster variables in a correct way, so that the variables I have in this quiver QF exactly go to the variables that they was correspond to, realizing QF as a subquiver in QGR. So let me tell you in 2 examples how this works. So this is the case of n equals 6. So we're in the flag 2, 4, 6, and the combinatorial map tells us to go to the Grassmannian 4, 8. The left-hand side, this is the quiver I get for the Grassmannian 4, 8, and the tableau. In this case, all the variables are Plukers. So that's why I only have 2 columns, 1 column each. I perform 2 mutations at these pink vertices. Maybe before that, you can already see that everything that is marked in green, so everything below here, these are tableau that are on the nose images of tableau coming from the flag, because I only have entries up until 6. And up here, these 3, these are also images of tableau for the flag, because 7 and 8 appear together. And these 5 extra tableau in the middle, they don't correspond to images of tableau from the flag, because I have either 7 or 8 appearing, but not together. So this is the part of the quiver where I would have to do something. And the strategy is quite easy. We keep all the green tableau that already have the right size. They're in fact already images of the initial tableau for my flag. And the rest here, I will do 2 mutations at 7 and 11. after I do these mutations, I get two-column tableau, but now they are tableau that I've been looking for, in the sense that they are images of the initial cluster variables of the flag, or initial tableau. So here I either have in a column 7 and 8 not appearing at all, or 7 and 8 appearing together. And after this mutation, to get the initial quiver for the flag, I just have to freeze this vertex and eliminate the three black ones. And that's the seed in the Grassmannian that was mentioned in the theorem. So let me show you one more example that is a bit bigger and shows more generally how this mutation sequence works. So the strategy that we have is giving an explicit mutation sequence from the initial seed of the Grassmannian to the seed that satisfies the conditions, that I can see the subquiver, the quiver for the flag as a subquiver, and that I have the tableau that are images of tableau of elements in the flag. So for this case, my n is equals to 8, and I'd consider the flag 2, 6, 8. Inside the Grassmannian 6, 12, which is where I would naturally land, filling up a 2 minor to a 6 minor needs 4 more entries, so that's why I go from 8 to 12. And in this initial seed of the Grassmannian, I identify the last 2 rows as already being a tableau corresponding to the flag. I've written them as rows here instead of columns, just to save space. And in the top row, I can already also identify 3 that correspond to images of two columns in the flag. And then this pink pattern in the middle is what we call the mutation grid. And this is where we're going to perform mutations, starting in the right bottom corner, going column-wise up. This is similar to a maximal green sequence mutation for the Grassmannian, just in a smaller pattern. And if we've done all these mutations once, what we find is that in the top row, the first 2 vertices will already be of the desired form. So they will be images of tableau corresponding to the flag variety. And then the next round of mutations, we're going to repeat the same pattern, just that we stop right before we would mutate at a vertex that already has a tableau of desired form. So if I do this mutation here, I end up with a quiver that looks like this. I've rearranged the vertices. So you can see, for example, 28 and 22 was inside my grid here, 28, 22. So I moved them to the other side. I will perform 3 freezings. That is, in n-5 freezings in general, so 3 in this case, and these 3 vertices. And after I've done that, you can see that the quiver splits into parts that are not connected. Like the mutable part on the left side is no longer connected to the mutable part on the right side. The right side is exactly the quiver for the flag variety, and the left side is vertices that I would eliminate. So there's this is known in cluster algebras that this is a very efficient way to kind of, or this is a good way to construct subcluster algebras. If you have a quiver that splits into 2 parts where the mutables are separated by frozens. And yeah, I think so that was all I wanted to mention on this mutation sequence and pattern. Are there any questions? Okay, so then let me just go to my last slide. So this is a little outlook of what would come next or what has been done. Going back to the original motivation with the physicists James Drummond and Glew, we checked that the cluster structure on the spinor helicity variety, so that's the case of the 2 n-2 partial flag variety. For n equals 5, it recovers the simple alphabets. In this case, the bootstrap program and other direct computations from physicists already computed the simple alphabet of the amplitude, and we could verify that that we can see it from the cluster structure, that it coincides with the cluster variables and a certain symmetry completion of the set. We have partial results on n equals 6, but the general problem for this in this program is that as soon as the cluster structure becomes infinite, we need to make like a clever choice of cluster variables where we're no longer need all the cluster variables, because in the symbol alphabet, until a certain loop, we always have a finite set of symbols, of letters. So there's some technicalities coming in, and the picture is not yet complete. Also, physicists right now are computing the alphabets with other methods for n equals 6 up until 2 or 3 loops. So we're kind of still waiting for those results to then check if we can see the cluster structure in the alphabet. Another interesting direction and very promising, or yeah, it looks like it will not be too hard to be done, is to generalize this embedding of tableau to arbitrary partial flag varieties. That's quite straightforward. And I have a student right now that is working on the conjecture of seeing if the cluster structures are also compatible in this case. And then there's two more applications that also go in the direction of physics. One is related to the momentum amplituhedron. So the amplituhedron is another attempt to compute the cluster, the scattering amplitude from a semi-algebraic set and its canonical form. This is called positive geometry, or conjecturally a positive geometry. And the cluster structure plays a role in these computations as well, or in understanding the combinatorics. And it seems that for this special case of momentum amplituhedron, the cluster structure and the spinor helicity variety is exactly what would be needed. And then the last open direction is to generalize this program also for having scattering processes with massive particles. So yeah, I'm also working with some physicists in this direction. And that's it. Thank you very much for your attention.